Hi, everyone. I have to admit people into the meetings. I'm gonna keep looking to see as people join. How's everybody doing?
Doing okay.
Doing okay? The sun's out, that helps, right?
Yes, it does.
Hi, Professor. I don't know.
I have a question, Professor. I don't know if I should wait for the whole class is here or not.
Your speaker is on, Professor. Your microphone is off.
Yes. I want a class.
Thanks for, okay. So before I forget, I want to tell you guys that YouTube has been taking a really long time to convert the Zoom videos, and sometimes it fails. So I apologize for it taking a while to post them, but I'll keep at it. It's just it takes at least half an hour, and then sometimes it fails, and then I move on to something else, and sometimes I forget to go back to it for a while. So you guys are now looking at my PowerPoint for the lesson plan, right? That says day 17?
Yes.
Okay, good. So I posted I updated the slides for chapter 10. There's a couple videos added on. I may add one more. I think it's pretty complete now. There's fewer videos in that than there are in chapter 9. I think it's a little bit easier to read that material than the chapter 9 material. Don't forget that the homework 8 for chapter 9 is due Friday. How's that going? You guys can type or speak your.
Yeah. It's going.
It's going.
Professor, I have a question for chapter 9.
Uh-huh.
You know, it's on page 297 where they talk about the principal shells like N1, N equals 2, N equals 3, equals 4.
Uh-huh.
Then they have the subshells associated with it. Like for N equals 3, it's a S, P, and a D.
Uh-huh.
For shell N equals 4, it's S, P, D, and F. Now, when you go to something like N equals 5 or 6, what is it then?
Oh, you know what? We just have S, P, D, and F.
Okay.
In theory, there are more available according to the selection rules, but we never touch on that.
Okay, so as far as N equals 4, those 4 subsets, don't go any further than that.
Yes.
Got it. Okay.
Wait. Say that again. Sorry.
When you get to N equals 4, you have the S, P, D, and F subshells.
Yes. Yeah.
You have 4 subshells, S, P, D, and F. I was asking about principal shells beyond 4, like N equals 5, N equals 6, N equals 7. What are those, and they'll have like 5 subshells, 6 subshells, or 7 subshells. And what is the letter specification for those subshells?
Oh, there's none for 6.
None for 5?
Or so you're saying if I have N equals 5?
Yes.
Let's see.
It's on page 297.
Well, let me get through the announcements first. Okay. Okay. So for this, oh, there was one link missing on the chapter 9 slides. It's another example of doing electron configurations. So I added a link to that. And I'm going to recommend, to get comfortable with the material, you really want to work as many end of the chapter questions as you can, because they come at the material in different ways. So remember, all the odds you have answers to. And my plan is to work some of those today after we get through all the questions. For Monday, after you've done the homework on Friday, for Monday, look through the chapter 10 slides up to VS EPR. And I would recommend doing a quick check on there's some questions on slide 29 that will be helpful. And I still have to post homework 9, but I would recommend, it's always good to get started on it before we meet so that you can have questions to ask. And then if you can remember, bring some kind of ball, like a orange or an apple, and some toothpicks to the session on Monday. There'll be some thought experiments that we'll do that I think will help you understand the shape of molecules. Okay, so back to the subshells. Let me see if I can do a different screen share. Okay. So Bill, your question is about the energy levels, right?
And once you get past the principal shell n equals 4, what are the subshell designations, you know?
They're the same. 5 and 6 are the same. 1, 2, 3, 4, 5, 6. Yeah, they're all the same as 4.
Well, okay, I got you. I see now. I see the light.
Oh, good.
I see the light. I see the light.
Okay, and I have a question that is asking from the homework, why do group 1 elements tend to form +1 ions and group 7 elements tend to form -1 ions? So let's look at that. It has to do with the electron configurations. So the group 1 is this first column here, and they all have the same last electron subshell, that's same last electron added. So if we look at the electron configuration for sodium's electron configuration, we can abbreviate. This is a little bit off. I have to go down here. We can abbreviate using the previous row noble gas, right? So the electron configuration for sodium is neon. And then the last electron added is what?
3s1?
Yeah, right, because so all of the elements in this row or in this column, the last electron added is an S1. So remember, there's a special stability with having a noble gas configuration, and that is neon's configuration. When sodium loses 1 electron, it loses the 3s electron. And when it does that, it has more protons than electrons, and it becomes positively charged. And now its electron configuration is the electron configuration of neon, which is very stable. Because this electron configuration is very stable, sodium tends to become a +1 ion. And it's the same for all of the elements in that column. So if I do rubidium, what noble gas would I use for rubidium's abbreviated electron configuration?
Krypton.
Yeah, so it would be krypton, and then it would be 1, 2, 3, 4, 5, 5s1. And when it becomes an ion, it will it'll lose an electron, and it will lose the 5s electron, and it will become, oops, do it in the same way. It will become rubidium +1, and now it has the electron configuration of krypton. So the short answer, well, I guess the short answer to all of that is that group 1 elements become +1 because when they lose an electron, they obtain a noble gas configuration. And the other question is, why do group 7 elements become -1? It's also because when they become that kind of ion, they obtain a noble gas configuration. So if we look at iodine has the electron configuration of krypton plus, what is that? 1, 2, 3, 4, 5. 5s2, 4d10, and then it is 5p5. It's right here. If it gets 1 more electron, it will have more electrons than protons, and it becomes I-1, and it will also have the configuration of xenon. So if an electron comes in, we get I minus, and I minus has the configuration of xenon, which is stable because it's a noble gas. Does that help?
Yeah, that was awesome. Thank you.
I rarely get a rating of awesome. Thank you. Okay, what other questions do you guys have? You can type if you don't want to talk, or you can just speak. You guys want to work some end of chapter questions? How do you feel about the material? Give me like a 1 to 10 in terms of comfort level, 10 being like super comfortable and 1 being terrified. You can type in.
I give it about an 8.
8?
Same.
That's not too bad.
See, once
You guys think you need more time with the material, you just got to get up to speed, or are there some gaps?
well, I think it's like you said, once you start getting into the gist of this and figure what's going on,
Just
it
takes-
tends to fall into place.
Yeah, oh good. Okay, the hydrogen homework problem of emission spectrum. Is this the Balmer series? Let me see if I can find it. Whoa. Uh-oh. 6er, I'm fine, can just never. Let me see if I can find the, you know what number the homework question is? Oh. Let's see, I'm gonna see if I can pull it up. Is it asking for the change in energy? Yeah, I'm getting there. Well, so far you guys have a high average score in there. Okay. You guys are still looking at the, let me see if I think I'm getting it. No, this is order of elements in size. You have the question number. It's asking to match the transition. But it's, I think, it's not number 3 for me. There should be like a, it should say like chapter 9. Let me see what I see. (9.41). Okay. Okay, here we go. Two of the emission wavelengths of hydrogen are 410 nanometers and 400 and 434 nanometers. One of these is due to the n equals 6 to n equals 2 transition. And the other is due to the n equals 5 to the n equals 2 transition. Which wavelength goes with which transition? Okay. So,
N6, N equals,
so E, hold on. Okay, you guys can still see my whiteboard, right?
right,
Okay, so E is equal to HC over lambda. And we have two transitions. One is a transition of 3 jumps, and one is an energy transition of 4 jumps. The longer the wavelength, the lower the energy, because lambda is in the denominator. Which transition will have the bigger energy change? One bigger energy change, the one that jumps 3 or the one that jumps 4?
it jumps 4.
Yeah, so this will be bigger energy. A bigger energy difference. And so then, and remember that if you have long wavelength, it's low energy. If you have short wavelength, it's high energy. So which one will have, which of these two will have higher energy? 410 or 434?
410.
Yeah, this will be higher in energy. So that should correspond to the N2 to N equals 4. Let me see. Yeah. That one was kind of a tricky question. Do you guys want me to go over that again? Okay, so let me just summarize. So we had one where n was going from 3 to 6. Was that what it was? Wait, we have one going from energy transitions. And we have n from 2 to 6 and n going from 2 to 5. This one will have a bigger change in energy because it's going further up the ladder. This change in energy will be smaller because it's making a smaller jump. And then we have to look at the energies associated with our 2 transitions. And for a delta E with 410 nanometers will be greater than the delta E corresponding with 434 nanometers, just because it's smaller wavelength. So that means higher energy. And that means it will go with this guy. I think that's the toughest question in the homework to sort of grasp. Any other questions, you guys? I've got some questions from the end of the chapter that I thought were good. Let me pull up this. Okay. I'm gonna erase this. Let me see. Can you guys see number 89? Ooh.
Yeah.
Uh-oh, what did I just do? I just did something weird. Ah. Let me see if I turn it off and I turn it back on, what happens. Okay, I'm back here. Let me share the screen again. I want to zoom in a little bit. There, okay. So now you guys can see number 89, right?
Mm-hmm.
Okay, so that question is, what is the maximum number of electrons that can occupy the n equals 3 quantum shell? So how would you approach that? So this is all the electrons that have a quantum number of 3. And we know that that every orbital can hold 2 electrons, right? So if we know the total number of orbitals with n equals 3, then we can calculate the number of electrons. So how many orbitals, oops. How many orbitals have n equals 3 as their quantum number? What are the orbitals with n equals 3? What are their names?
NS and NP. I mean, 3S and 3P.
Yeah, there's 3s, and there's one of those. There's 3p, right? And there's 3 of those.
Mm-hmm.
And then we also have 3d, right? 1, 2, 3, 4, 5. Those are all the orbitals with a quantum number of 3. Each orbital can hold 2 electrons. So 1, 2, 3, 4. Oops, I'm going to fill them in the right order. So that's 8. And then the Ds can hold 10. So it would be 2 plus 6 plus 10, that's 18. That's the maximum number of electrons that can be in the n equals 3 quantum shell.
Professor, just as, and looking at that,
Uh-huh.
when I look at the, there on that n equals 3 principal shell, there's no D's across that periodic table. It goes
Correct.
from
Because
3s2 to 3p. So you're but the D's do count, even though they don't show up in the periodic table.
yeah, because it's saying what has n equals 3, and the 3 Ds, they're in the row below it, but they're there.
Okay.
Yeah.
Okay.
Okay. I'm trying to do evens because you guys don't have the answers to those. What is the electron configuration for P3 minus? See if you can do that. Okay, so for 3 minus, it's going to be P3 minus, it's going to be the electron configuration of phosphorus plus 3 more electrons. Right, and do you guys want me to type in, do you want me to do it from the beginning or with the abbreviation?
It makes a difference.
No difference? That's good. Okay, so I'm gonna do, I'll do it just because we haven't done any from the beginning, I'll do the whole thing. So it's 1s2, 2s2. Let me see if I can. I gotta move this over. Okay, 1s2, 2s2. Then I go to 2p6. And then 3s2. And then I go across. And when I get to phosphorus, it's 1, 2, it's 3p3, but then I'm going to add 3 more, and so it's 3p6. And we could also write that as neon. That's the noble gas in the previous row, and it would be neon 3s2, 3p6. Well, I guess really what we should do is write it as argon. Okay, level of comfort with that from 1 to 10, you guys.
About
Oh,
an 8.
8?
I give it an 8.
Oh, why? It's 3p6 because, so phosphorus, I'm going to abbreviate. Phosphorus would be neon 3s2, 3p3. Does that make sense? But if it's p3 minus,
3 more electrons.
it's got 3 extra electrons. So that makes it
18.
3s2, 3p6. How many valence electrons does phosphorus have?
Like 6, 8.
The 3 minus has 8 valence electrons.
Okay, yes. So it's going to be 5.
Yeah, 5 for phosphorus by itself.
So, Professor, can you state that question one more time? You said how many valence electrons
How
does
many?
phosphorus have?
Yeah, how many valence electrons does phosphorus have?
Now, could you ask the question, how many valence electrons does P3 minus have?
I could, yeah. It's not as interesting because it's got a full shell.
Okay, but that would be 8 for that question.
Yeah.
Okay.
Okay, I'm gonna erase this. I'm gonna write an electron configuration which is not a good one, and I want you to tell me why. What's wrong with it? Oh, there's lots wrong with that.
Lots wrong with that thing.
What's wrong with that?
Well, for one 1s, you can only get 2 electrons in it.
Yep, only 2 here. Same thing here, right?
Right.
What about this one?
I think it's 6 only.
Yeah, only 6. So each subshell has too many electrons. That's what's wrong with that. This is question number 98 at the end of the chapter. 97 has more examples that you'll have the answers to. Okay, what about 1s2, 2p6, 3s2.
I think that was good to go.
This one?
I,
So we want the ground state electron configuration. That means the lowest possible energy state.
mhm.
So we have to list the orbitals in order
Right.
from lowest to highest.
So you're missing 2s2 out of
Yeah.
that?
So let's calculate. So there's 2 plus 6 plus 2 electrons here. That's 10, right?
Right.
So let's put them in the right order. It would be 1s2, 2s2, and then
Yeah.
what comes next?
2p?
2p, and we have 6 left, so it'd be
Yes.
2p6.
Right.
Okay, so so Javier has a question. Once it has electron configuration of argon, it no longer has valence electrons. Argon, we would say, has 8 valence electrons. We would say it has a full valence. It has an octet. So it's actually worth pointing out that this electron configuration is allowable. But it's not the ground state. This would be an excited state. Meaning that orbitals are filled not from lowest to highest energy. So this is allowable, but it's not the ground state. This one is the ground state. So I've got a question for you. If this is the ground state, what element is this?
Back.
Bill, you're carrying the class.
It's an electron, so
They owe you.
they owe me.
Yeah, so that's right. That's the thought process. So if I ask you what element is that, what you'd do is you'd say, okay, how many electrons does it have? It has 10 electrons. And if this is zero, if this is not an ion, then it has to be neon.
Yeah.
Okay, let me ask another question. Okay, let's imagine we have something that it's a 3+ ion, and it has the electron configuration of 1s2, 2s2, 2p6. What is the what ion is this?
Nitrogen?
Well, it's 3+. Nitrogen tends to be 3-.
Oh, okay, right. Okay.
Yeah, so that would actually be correct for 3-. Okay, so if I should probably just fold this. Let me fold it a little better. Okay, so if I am looking for something with a 3+ charge, it's generally going to be in group 3. So notice the group numbers are labeled for, at least some of them are labeled for the number of valence electrons they have, but also on the plus side there, the charges that they get. So group 3 tends to be 3+. If boron loses 3 electrons, that would bring it back to 1, 2, 3. It would have the electron configuration of helium, which would just be 1s2. If aluminum loses 3 electrons, it would lose 1, 2, 3. It would have the electron configuration of neon. And that's what this electron configuration is. So the ion would be aluminum 3+. Oh yeah, good job, Drew. And so when an ion is requested, make sure that you indicate the ion symbol, which would be aluminum 3+. And you could just type it in like Al 3+, because we don't have, well, that looks bad though. Yes, David, you can go. Let me see what else there's some more questions in 98. Here's another electron configuration we're looking to convert it to the ground state. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4d10, 4p3. We want the ground state configuration for this atom. So what's going on here? What are we missing? You guys can type.
You're looking for the
Yeah,
element associated with this?
we're missing, so what's wrong? Drew answered. It's we are missing 3d10, right?
Right.
We went 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. That's all fine, but this should be 3d10. And then that will be the correct electron configuration for the ground state. Uh-huh. Okay, which element is this?
Tim. Arsenic?
What is it? One,
Yeah,
two.
arsenic?
Yeah, it is. Good job. And so there's 2 ways you could do that. This way, first way would take longer, and that is to count all the number of electrons, and then assuming it's a neutral element, we go to that atomic number. The other thing is we look at, in the ground state, the last orbital to get filled, and that's 4p3. So you'd go to where the 4p electrons get filled, and that is 1, 2, 3, 4, and then 1, 2, 3. And so it would be here.
That's flick trick.
It helps when you're lecturing. Okay, let me see. Oh, you know what we haven't dealt with? Let's talk about periodic trends. Okay, so for radius, you have to worry about two things. When you go from left to right on the periodic table, and when you go from top to bottom. So this is the size of the radius of each atom. I think going from top to bottom is a little bit easier to understand. As you go, when you start from helium and you go further down the periodic table, that's top to bottom, the radius increases because you're getting more and more shells. From left to right, I think it's a bit trickier. So when you go from left to right on a row in the periodic table, say you start at sodium and you go to argon, you're adding electrons to the elements, right? Magnesium has one more electron than sodium, aluminum has one more than magnesium, and so on. But you are also adding protons. And because of that, the protons pull the electron cloud. There's more positive charge in the nucleus. They pull the electron cloud closer to the nucleus. So as you go from across the periodic table from left to right, the radius actually decreases. I'm trying to, what other, okay, ionization energy. Let me move this out of the way. Okay, so ionization energy. Ionization is, you have some element, some atom, could be anything, and you give it energy, and the energy is enough to kick an electron out of the atom, and you wind up with an ion. So the more energy that you need to add to eject an electron is a statement of how tightly held the electrons are to that atom. Which group has the most loosely held electron in its valence shell? You can type your answers.
Man, it's gonna be.
The metals, yeah, which ones though? Which group likes to become +1?
The
Alkaline metals.
alkaline metals.
Yeah, the alkaline metals, and then after that, the alkaline earth. So, and that's because they get the noble gas configuration. So, as you go from left to right on the periodic table, the ionization energy increases. So, so the ionization energy for sodium is less than the ionization energy for chlorine. And the way I sort of remember it is sodium wants to be Na+. So it will have a low ionization energy. Chlorine is stable as chloride, the anion. So it actually wants to gain electrons, not lose them. So it's going to have a very high ionization energy. Okay, the other thing is to think about ionization energy and going from top to bottom on the periodic table. So we have our positive nucleus. And every time you go down a row on the periodic table, think of it, it's a little bit simplified, but think of it of shells of electrons. Right? Okay. So in our most outer shell, the electron is being held to that atom by this positive nucleus. Now imagine an electron that's only in the second shell. And this outer electron is also being held by the positive nucleus. Which one is going to hold its outer electron more tightly? A or B?
A.
Yeah, A. Why?
Because they're closer to the nucleus.
Yep.
And because of that, they're going to hold on to them more.
Yep. So because these electrons are closer to the nucleus and there's less negative charges in between this electron and the nucleus, that's called shielding. This is going to be held more tightly. That means it's going to require more ionization energy to eject the electron. These are loosely held because in between this positive charge in the nucleus and the negative charge in the outer shell, there's all these minor repulsions in between. That's called shielding. And so this has lower ionization energy. So as you go from the top of the periodic table to the bottom of the periodic table, ionization energy drops. Okay, so let's try a couple questions. You guys got this? Any questions related to this? These are the kinds of questions you would get asked. Choose the element which is bigger, Sn or Si. Silicon or tin? Which one's bigger?
Tin.
Yeah, because it's down the periodic table. What about silicon or phosphorus? Which one's bigger?
Silicon.
Yep. Okay, so you guys feel okay about periodic trends? Thank you, Leah. What's the scariest part of the chapter?
Not really.
It's okay?
It's okay.
Go ahead.
For me, it's better than what we covered in the past.
It's what?
It's better than what we covered in the previous chapters.
Oh, yeah.
For me, anyway.
Okay. Okay. All right. I think I've covered everything I want to cover. Oh, here's one. One more. Arrange the elements in order of increasing atomic size. CS, SB, S. Oh, this one's easy. Let me see, S. I just lost where I was.
CS.
There's one more. Oh, and SE. PB and SE. So it says increasing order and increasing size. So make sure that you understand that if you're putting it in order of increasing size, you put the small one on the left and the large one on the right. So among these,
I think CS is going to be the largest.
yeah. Then what?
Okay. S, PB.
Oops, I crossed out the wrong one. Lead will be smaller, right?
Where's lead? Yeah, I'm hung up on my. I'm slow going through the periodic table here.
Yeah.
Still
Well,
looking for lead.
here's cesium, here's lead.
Okay.
Yeah.
Let's see.
So lead will be smaller.
Lead be the next one down.
And then, and I would put, let's see, antimony's here. Where's selenium? Oh, selenium here.
And sulfur.
And then sulfur. Yeah. Cesium.
No, the ones
This one is number 84. There's a similar one, 83, that you'll have the answer.
so on this
Mm-hmm.
this thing, the one that got me to thinking the most about it is when you had one, like say you had oxygen,
Mm-hmm.
and then you went over to something like phosphorus. You couldn't
Mm-hmm.
tell
Yeah.
which one was. I guess that's when you can't really tell which one is larger, can you?
In general, the row jump is going to make a bigger difference than going from left to right.
Okay, the road jump makes a bigger difference than left to right.
Yeah.
I know the book had a few of them. They couldn't. The answer was you couldn't tell which was which.
Oh, huh. Which one was that?
I can't. Let me hang on one moment, Professor. Let me see if I
I
can.
didn't know that was an option.
It was an option. Bear with me and see if I can find one.
It was in the chapter?
Yeah. Yes. Here's one here. SN to BI.
What page is it on?
Oh, wow. Okay. I don't know exactly what page it was
Oh,
on.
okay. Oh, here it is. I see on 308,
Yes.
308. SN to bismuth to,
Right. And the answer was cannot be determined based on periodic properties alone.
oh, all right. Well, then why would it give that other question? SN to BI, which one is bigger?
But as you go to the right, they become smaller. As you come down,
Right.
they become smaller.
No, as you go down, it gets bigger.
It's
Yeah,
bigger.
so we've got two
To the
conflicting.
right, it's smaller. So that kind of hung me up.
Oh, so I got a question. Why is cesium bigger than lead? So lead has bigger mass, right? Because it's got
Right.
82 protons, but the atomic radius decreases as you go from left to right
Right.
because there's more protons in the nucleus, and those protons pull the electrons closer to the nucleus. So as you go from cesium to lead, lead is smaller.
Yeah.
Tin to lead, tin is smaller.
Right.
And it has to do with the fact that there's a bigger nuclear charge pulling the electrons closer. And it seems counterintuitive, but think like you have this super dense nucleus and the electron clouds are really diffuse. And they don't have much mass. So it's a little bit easier if you think of it as this diffuse cloud that having more and more charges is going to pull it closer to the nucleus. If you thought of it as some dense material, it's harder to imagine, but remember, this is a really diffuse cloud with no mass. And so the more positive charges in the nucleus are able to attract it more. Okay, I think I've covered everything you want. If you guys have any questions, I'm happy to answer. Otherwise, and feel free to email me questions on the homework. I'm spending a lot of time on the computer these days. Okay, so I think I will end it there. We have lab at 11:30. And make sure you have the pre-lab done before that. And you can get started on the other part if you want to. I don't have much of a pre-lab lecture because I think it's pretty self-explanatory. I was just going to go over a couple things about the semester at the beginning and then set you guys free.
Professor,
Yeah?
question on the pre-lab coming up.
Uh-huh.
In the manual, they had okay, you have a pre-lab that we answer and then submit, correct?
The pre-lab that is in the manual is exactly what's online.
The thing is, the pre-lab in the manual, on the backside of that page, it had a balance equation. They wanted a completed iconic equation and the net equation. But when you went online and did it, that particular problem did not show up.
Oh, well, that was probably because I didn't turn the page when I wrote it.
I didn't turn the page either, so I started looking at it.
Oh, so
Then I
don't worry about it then.
got it.
Yeah. Oh, and Bill, the question about the drops, it's in the data.
The drops.
You asked about the
Oh,
acid
the
base
drops.
drops.
Yeah. Okay.
It's in the data.
It's in the data. Okay.
Yeah, you're not going to get it from the video. You get it from the data.
Oh, okay.
Yeah.
That answered my question.
Yeah. Okay. Well, thank you everyone. And I will be back for those of you who are in lab today, I'll be back at 11:30.
Thank you.
Have a good day.
See you then. Bye.
Great job hanging in there. Great. Bye.
Bye.